Fine. So we are talking about stars, right? So let us draw a representative model of a star. So this is a star, right? Approximately model. Now, what is inside this star? Particles, right? Gas particles. So basically, gas particles like hydrogen, helium, and other elements. Now, these gas particles can be either neutral or ionized. Both are possible, right?
Sir, excited type.
Ionized or excited, right? Now, excited comes within the purview of neutral, right? Now, also we have got photons inside this star. Okay. Also, during nuclear reactions, what are formed? Neutrinos. Neutrinos are also formed. Now, when I am talking about gas particles, I am talking about neutral and ionized. Now, when ionized, as a result of ionization, electrons will also be emitted and bear nuclei. So, we have got how many types of particles? See, electrons, neutrino, photons, bare nuclei, then neutral nuclei. So many type of species are there inside the star. Okay. Now, what about the pressure due to all these particles? What about them? But before I talk about them, it is important to know that these gas particles, all of them, and this, all of them, they are fermions. Their nature is essentially fermions. Even if I am talking about nuclei, inside the nuclei we have protons and neutrons. Each of them are fermion. So we are talking about fermions here, effectively. However, this one, this is basically boson. This photon, right? So basically, if I talk about the species inside the star, we have got fermions, all this group, and also we have got bosons, which is these photons, right? So this is the overall structure. Now, if I am going to talk about the pressure inside the star, right? Then I have to talk about the pressure due to each of them, right? Now we have already talked about this. If we talk about the ionized particles, taking into account the electron, then we simply have the gas pressure, right? Here I am neglecting for the time being the neutron, but we also have pressure due to the, neutrinos. Also have pressure due to the neutrinos. I am neglecting it for the time being. Similarly, for the photons, we have got radiation pressure, right? Pressure due to radiation. Good. Everything is fine. Now, what is happening inside the star? Basically, as you know, the pressure is maximum near the central part and slowly the pressure decreases outwardly. This is one of the reasons, or I should say, if you look at the hydrostatic equilibrium equation, there is a negative sign. This basically signifies that with increasing R, the pressure slowly decreases. Right. Okay. Now, we also know that in the central part, since the pressure is high, the temperature is high, so upon certain conditions, if they are met, if the temperature is very high, then through quantum mechanical tunneling, nuclear fusion can start. Right? This we know. And as a result of the fusion, something interesting happens. What is that? The composition starts to change. Right now, before the fusion, whatever is there is there. There is no changing of one particle to other particle over here. But as a result of fusion, hydrogen gets converted to helium, helium to carbon, and so on. So slowly and gradually the composition changes. This is one of the results of fusion. Right? Now, okay, fine. Now, let me talk about again the pressure which I was talking about. So, there are basically two types of pressure. One is the gravitational pressure pushing it inside, and then the gas pressure. What is gas? Just I talked about the pressure due to all the particles inside it, including radiation pressure, right? All of them they are pushing. So, this is basically radiation pressure plus gas pressure, and here we have got the gravitational force. So this is how the things are playing around. Now, at the end of the fusion, say for a star, hydrogen fusion, helium fusion, and so on, you know that at the end of it, we have got an onion-like structure, right? If the star is very massive, then very at the core we have got iron, and above that we have got silicon, oxygen, and all that. The important thing is that at some point, whatever be the mass of a star means fusion must have happened inside this self-gravitating gas ensemble, sort of. Fusion must have happened. Now, ultimately, fusion will stop. It will not go on forever. What happens after that? After the fusion has stopped, there is no source of energy generation due to nuclear reaction. So slowly and gradually what will happen after the stopping of fusion, this force, it remains the same. I am assuming the mass remains the same, but this force keeps on decreasing, right? Because a major part of this radiation and gas pressure is due to the energy also released due to the fusion. So fusion is giving away energy. That energy somewhat increases the kinetic energy, photons energy, right? All that. So slowly this thing keeps on decreasing. Now you can easily see the result. The gravitational force is much larger. So slowly this star will contract.
Collapse.
Sort of collapse. Keep on contracting. So why doesn't it contract? That's the next question. Now for that we have to understand that during the collapse, what will happen? Let us talk about two particles. Slowly their distance keep on decreasing. If this is one particle, this is another particle, the distance keep on decreasing. Fine, decreasing. Now they are coming very close. What after that? Now when I am saying close, I have to talk in language of physics. So distance becoming close means that now the separation between the two particles becomes close enough to the de Broglie wavelength. Right? Average de Broglie wavelength of each of them. What will happen if such a thing happens? Till now, this entire scenario, this was classical. And we're talking about non-relativistic, non-degenerate, okay, ideal gas. This is not a van der Waals. Real gas where we have got van der Waals force between the particles, right? Now, as the collapse happens and the particles come close to each other, slowly and gradually, one of the assumptions will be violated. That is, it no longer remains classical. It will start entering the quantum regime. That is, the distance becomes close enough to de Broglie. Okay, now what happens? We have got two types of species, fermions and bosons. Right? Now for the time being, let us assume that all of a sudden a collapse happens. everything collapses. What does this mean? Effectively, this means that all the species of particles inside the star, previously they have got all different energies, different quantum numbers, but as a result of the collapse, now all of them have the same sort of energy or quantum number. Now they are residing in the same level where all the quantum numbers are the same. This can be okay for bosons but not for fermions. Remember Pauli's exclusion principle. Okay, now again let us look over here. So, as they come close together, the quantum regime, now their manifestation, the type of the particle becomes important. For bosons, photons, there is no problem, they can come close together. Right, but for fermions, say electrons, neutrons, protons, they cannot come close together because of the Pauli's exclusion principle. And this very fact that they cannot come close together, this in a way creates a restrictive force, a restrictive pressure, and this pressure is now known as degeneracy pressure. So the situation is like that, it keeps on decreasing. So this whole star, now this collapses to a certain point like this, but now here the degeneracy pressure counteracts this gravitational force. The two becomes equal. This is the degeneracy pressure. Now remember, how many species were there inside the gas? We have got neutron particles, ionized particles, we have got electrons, right? Then we have got photons. Each of them will have its own pressure. But the degeneracy pressure, remember degeneracy means I am talking about de Broglie wavelength. That is lambda is equal to h by p or h by mv, right? Now mass, consider the mass of each of them. Forget photons, I am talking about these three particles. Mass of each of them. Whose de Broglie wavelength will be larger in this? Electrons de Broglie wavelength will be larger for the same velocity because its mass is much smaller than the protons and neutrons. So this means that of all these three particles, neutral particles, ionized particles and electrons, free electrons, the electron de Broglie wavelength will be the largest, and as I am coming close together, it will be the electrons whose degeneracy pressure will now come into effect. You understand this thing? So here the pressure will be basically, pressure is equal to pressure due to electrons, and this will be degeneracy plus pressure due to other particles, and those will be again non-degenerate or classical. This is important. So inside the gas right now, other will be remain the same as it was previously. However, for electrons it becomes degenerate because their de Broglie wavelength is much larger compared to the de Broglie wavelength of protons, neutrons, other nuclei. And this time it is this number, this is very large, and this counteracts the gravity. And when such a thing happens, this is the regime of white dwarf. Okay, remember no fusion. Right now there is no fusion at all. This is the regime of white dwarf. Next, suppose the mass of the star is very large. What will happen? If the look carefully, if the mass of the star is very large, then this has a restriction also. There are finite number of electrons, mass of the star is very large, then what will happen is that this degeneracy pressure will not be able to counteract gravity. So this will keep on decreasing, keep on collapsing, and now, so keep on collapsing. So even smaller. But this time, out of all these three, we have got neutrons and protons, remember? So neutron, proton and electron. Now look, what will happen this time? It will be the de Broglie wavelength of these neutrons and protons, which will come close together to the interseparation distance. And now this pressure, which will counteract gravity, this degeneracy pressure will be due to neutrons or protons, because this time they will become very large. বুঝতে পারছো? And when such a thing happens, again we will have hydrostatic equilibrium. So hydrostatic equilibrium occurs in three parts. First, when we have a normal star, gravity and pressure, gas pressure, when they become equal, we have got hydrostatic equilibrium. Okay? There is no contraction or expansion. Next, when we have got degenerate electronic pressure, this counteracts gravity. This is the region of white dwarf. This is a normal star, main sequence star. Okay? And this is the region of white dwarf. And now, if the mass is very large, then we have got degeneracy pressure due to neutrons, which will counteract gravity, and this is the region of neutron star. So see, three situations for hydrostatic equilibrium. Now you understand the importance of degeneracy in stellar evolution, because here in these two scenarios, the white dwarf and neutron star, this cannot exist, you can say, if there is no quantum manifestation. Okay, and here hydrostatic equilibrium is happening. That is, these structures, these objects exist because we have got Pauli's exclusion principle, because of the manifestation of the fermionic nature of particles. Okay, so this is very interesting. We have done a sort of comparison between normal star, white dwarf and neutron star. Now what happens inside, we will talk in details. Right, any questions?
White dwarf, neutron star,
Yes.
black.
Now you might be thinking that this is where the story ends, but actually this is not where the story ends. Okay, because even smaller than neutrons, we have got quarks, right? So theoretically, we also have a quark star. Quark star. Yes. What is a quark star? This is a theoretical concept. Its mass is very large. If the mass of the star is very large, such that even the neutron degeneracy pressure is unable to counteract the gravity, then the star will keep on collapsing. Now what will happen is that the protons and neutrons, from inside them the quarks will come out, right? And then there will be degeneracy due to these quarks, and again we will have hydrostatic equilibrium, and then we have this quark star. So theoretical possibilities 4. This is the fourth one, quark star. Now if during this situation some transformation happens and we have got strange matter, then we have got strange star as well. Now I am not talking about it. So basically we also have a strange star. Strange star, where sort of hydrostatic equilibrium happens and there is certain finite number of strange matter. Okay, now these two are sort of hypothetical. There has not been experimental evidence as of 2024 December, right? But in future we can have, or maybe we can have some more possibilities, dark star and some other star, more exotic star, but overall these two are exotic structures. Okay, so this is all about hydrostatic equilibrium. So basically we are talking about these 5 classes of possibilities for hydrostatic equilibrium. So basically there are 5 such possibilities. You have to understand 5 such possibilities for hydrostatic equilibrium in star. Remember, in this entire situation, here I am not talking about fusion is actually happening over here. In these two objects, there is no fusion. Again, no fusion over here. Possibly fusion is happening over here as well. So if I am talking about fusion, probably here fusion is happening and here definitely fusion is happening and here no fusion. So you see, even without fusion, we can have a stable object. But this time, the quantum nature helps in maintaining the hydrostatic equilibrium, right? That is the fermionic nature, which basically means that there is a sort of degeneracy pressure. Okay?